Okay, welcome everyone. I am Mark Gauker from the Advanced Technology Division at Lincoln Laboratory, and I want to give a great welcome to everybody for the kickoff presentation for the Nano Explorations seminar series. Today, we're very pleased to have a talk by Avery Rosh from Lincoln Laboratory to get the series started. So the ground rules for today is that please hold all of your questions until the end of the presentation. And then there are three ways that you can ask questions at the end. You can add them to the Q&A during the course of the talk, and then we'll queue them up and read them off at the end. You can also use the chat, or if you want to ask them in person, just raise your hand at the end of the talk, and then you can ask your question live. So Avery is an assistant staff in the Advanced Materials and Microsystems group at MIT Lincoln Laboratory. Her talk is titled Radiation Shielding of Microelectronics via the Additive Manufacturing of Nanocomposites. Avery graduated from Bucknell University with a degree in chemical engineering in 2021. After graduating, she worked as a software engineer at Lockheed Martin in Colorado before joining Lincoln Laboratory in January of this year. Avery currently supports projects that develop custom ink formulations for 3D printing, create novel packaging materials for microelectronics, and synthesizes custom coating formulations. Outside of the lab, she is a student in the advanced study program at MIT, where she's working towards an advanced degree in material science. Okay, Avery, take it away.
Thanks. Okay, so as Mark said, I am going to talk about the radiation shielding of microelectronics via the additive manufacturing of nanocomposites. So if this wants to click, there we go. So basically, I want to start by explaining what MIT Lincoln Laboratory is. We are a DoD federally funded research and development center, which is an FFRDC. We are divided into a bunch of different mission specialties, anything ranging from biotechnology to air traffic control to cybersecurity. There are a few exceptions to being mission-based, and one of them is actually the Advanced Technology Division, which is Division 8. So the Advanced Technology Division, we create components that help support missions regarding national security. And specifically, what I am in is Group 81, which is the Advanced Materials and Microsystems group. We do things like AI-assisted materials, wafer scale systems, smart fibers, and textiles. Specifically, and from the title, you can assume, I work on additive technologies. So going through our outline of what we're going to talk about, I'm going to start with the radiation effects on electronics, move to additive manufacturing as a whole, ink properties, and then our radiation testing campaign. So first, the radiation effects on electronics. This is becoming more and more crucial in our development of electronics as we transition to small sats, which is defined as any satellite that weighs less than 600 kilograms. And they are becoming more susceptible to radiation damage because we are more densely packing our electronics on the system. So the likelihood that a radiation particle hits an electronic and causes damage is greater. But small satellites as a whole, despite this difficulty, has increased sixfold in terms of the number of spacecrafts launched in the last decade. In 2013, it accounted for 61% of our total spacecrafts launched, and in 2022, it accounted for 96%. And this is largely in part to constellations like the Starlink and the OneWeb. So we have this past trend over the last decade, but studies are showing that this trend is going to continue into the future, making it really important that we are able to protect our electronics if we want them to stay. So the natural space environment holds a whole host of hazards to really any electronic we put up there. Every time I do this slide, I always say it's a miracle that we are even able to maintain anything in orbit right now. And there are three main types of orbit. There's LEO orbit, which is the small one close to the Earth. There's HEO, which is highly elliptical orbit, and then geosynchronous orbit. Specifically, small satellites are going to be launched into LEO orbit. So I'm going to talk about some of the hazards associated with that. The big one is the Van Allen belt, which is trapped particles, specifically protons and electrons. Also, depending on where you are in the solar cycle, you have solar events and photons coming from the sun, which can cause damage. There's also galactic cosmic rays, which they basically exist in space and will damage anything in their path. So in history, actually, the greatest example of the damage that radiation causes to electronics is a man-made phenomenon. During the Cold War, the United States did a high-altitude detonation of a 1.45 megaton hydrogen bomb called the Starfish Prime. It created this artificial Van Allen belt, complete with the auras that were seen even from Honolulu. The radiation effects took down the accompanying 27 data collection rockets. 40% of the orbiting satellites, which in 1962 was only 9 satellites, but still that is a huge percentage. It also caused errors with the ground communication, electrical networks, people's alarms in their homes were going off. The radiation affected any electronic that it got near. And this is because if we break down our electronics to their base component of transistors, for example, which makes up the logic, we can explore 2 different types of radiation damage. So I'm just going to show you the cross-section of my little transistor schematic and show you that we have the silicon. Above that, we have the oxide insulator. We have the doped source and the drain and the gate voltage. So since this is a semiconductor, when activated into the on position, free ions will move from the source to the drain. If we're looking at our 2 different radiation effects, the first we have is total ionizing dose, or TID. This happens when radiation strikes the oxide insulator, causing charged particles and defects to form. These charged particles and defects cause the long-term degradation of your electronics over the mission lifespan. This is caused by gamma radiation or high-energy proton radiation. On the flip side, we have single event effects, or SEEs. These are caused when the radiation strikes the silicon itself, causing free ions to move to the drain, turning the transistor incorrectly into the on position. At the very best, this causes data corruption. At the very worst, this can cause instantaneous mission shutdown. This is caused by heavy ion radiation and high energy proton radiation. So electronics are present basically in every facet of our lives right now. So if we look at terrestrial electronics, such as consumer electronics or large area ground systems, we're able to use commercial bulk CMOS and commercial silicon on insulator transistor technology, because even though they have low radiation tolerance to both single event effects on the y-axis and total ionizing dose on the x-axis, they are completely sufficient enough for a terrestrial environment. When electronics advanced to the commercial FinFET, which is more efficient, it decreased the radiation tolerance of these electronics, which again is totally fine here on Earth. However, when we want to move to the commercial space system, we need to have additional protective mechanisms. Right now, these include indiscriminate bulk aluminum shielding or built-in redundancies. The idea is if you need one electronic, you send up 10 and hope that only 9 get destroyed over the course of the mission lifespan. But when we talk about our protective mechanisms, we need to talk about SWAP. SWAP stands for size, weight, and power, and then the -C is cost. In reality, the greater the size, weight, and power required for your satellite or your space system, the higher the launch cost is going to be. So overall, when we design anything, the ultimate goal is to minimize the SWAP-C penalty. So looking back at our current radiation mitigation options, let's look at the unprotected / the built-in redundancies. This has a really high SWAP-C penalty. It has a high weight penalty because you're sending up additional electronics, and it has a high cost penalty because you are making additional electronics. They're expensive. For bulk aluminum shielding, you have a high SWAP-C penalty because the aluminum increases the size of your satellite. So in turn, it increases the launch costs also. Additionally, aluminum is selected because it has good coefficient of thermal expansion matching with the rest of the satellite, in addition to it being cheap and lightweight for a metal. It's actually not a really good radiation shielding material. Because these were previously the only two options, over the years, people have looked into rad-hard devices. These are transistors and technology themselves that are resistant to radiation. Because of that, they have a low swap penalty. You don't need any additional shielding added to the system. However, they have a high swap C penalty because they're incredibly expensive. They also have very long lead times and often use outdated electronics. From a packaging standpoint, there is a commercial option called the Rad Pack. However, this does too have a very low swap penalty because the package and the device itself make it more radiation tolerant. However, there's very limited diversity of parts and low customization, which means if you want to use the Rad Pack, you also have to use the electronics that this company is selling. This led MIT Lincoln Lab to create our 3D printed radiation shields. They have a low swap C penalty. They are completely customizable, both in shield composition and placement. So it allows you to use any desired electronic device, including commercial off-the-shelf or COTS parts, and you could print directly onto the vulnerable portion of the electronics. Going into our future work, we want the same benefits as above, but we also want real-time gradation of our shields, in addition to an accompanying model to best select the shield shape and composition based on the mission, orbit, and life. Remember, we have HEO, LEO, and GEO. Moving through our outline, I'm going to talk about additive manufacturing. Our vision for additive manufacturing is the ability to print our shields directly onto the electronic. And this should greatly simplify device assembly because we are printing conformal to the electronic that we are implementing into the system. Additive manufacturing is actually a very broad term. It's anything that's not subtractive, traditional subtractive manufacturing done with a mill or a lathe. And it's the layer by layer fabrication of a three-dimensional object. So even though there are many different options to choose from, we opted to use material extrusion because it allows us greater diversity of materials and greater processing approaches. Specifically within material extrusion, we are using solvent casting direct ink writing. As you can see from the video, it is a robotically controlled arm using CNC code that prints our ink. Our ink is our material dissolved in a volatile solvent. So basically, once it's deposited onto the build plate, the solvent rapidly evaporates out, leaving behind a rigid structure. This allows us the ability to use multiple materials. As you can see, the blue in the print above, we can print whatever shape we want, and it's compatible with other techniques because it is pick and place. However, when we formulate our inks, we need to have two distinct requirements. Our inks need to be shear thinning, and they need to create a self-supporting structure. I'm going to explain these concepts for people on this video that are not material science experts. So to explain shear thinning, we are going to backtrack into Newtonian viscosity. So if we want to look at low viscosity, which is something like water, or high viscosity fluids, which is something like molasses, we do so in this parallel plate system. So if we apply a force to the topmost plate with the liquid in between and a stagnant bottom plate, we get a velocity of this top plate and it creates this velocity gradient. The velocity gradient is directly proportional to the amount of force that we are putting on. So if we add more force, this velocity gradient grows with it. And now if we compare the low viscosity and high viscosity systems, the velocities are the same, the velocity gradients are the same. However, the amount of force required to move the low viscosity fluid the same amount as it takes to move the high viscosity fluid is significantly less. I'm going to quickly change our vocabulary. If you divide force by area, you have shear, in this case, shear stress, which is represented by tau. We are going to assume that the two areas are the same. So we can say that the shear stress applied to the low viscosity fluid is lower than the shear stress applied to the high viscosity fluid. Completely the same principle as when we were describing this in force. So now we can plot our shear stress versus velocity gradient, and you get these two straight lines. The slope of these lines is the viscosity, and then you have the Newtonian viscosity equation, which is comparing your shear stress to the velocity gradient using viscosity as your proportionality constant. When we transition to fluids that don't follow these rules, we no longer use the velocity gradient as our x-axis. We're going to start using shear rate, which is defined by gamma. When we plot our shear stress versus shear rate for Newtonian fluids, we have this linear relationship. However, we have shear thinning and shear thickening, which are non-Newtonian and non-linear relationships. To explain these, I want you to think of an old school ballpoint pen for shear thinning. When you take the lid off, your liquid doesn't flow. It is too high viscosity to flow out of the ink. However, when you apply a force onto the, you decrease the viscosity enough to write on your page. On the flip side, we have shear thickening. This is something like oobleck, which is a cornstarch and water suspension. Suspension means that the cornstarch doesn't actually dissolve. It just kind of is particles dispersed throughout the liquid. When you apply a low shear stress on the system, it is a low viscosity fluid. You're very easily able to mix it. However, when you apply a high shear stress on the system, you dissipate the water out and basically the cornstarch contracts into this sludge. So you have a really high viscosity liquid. So if we look at our viscosity plot, we're going to change this. Instead of doing shear stress versus shear rate, we're going to look at this the way a rheometer does. So a rheometer has two parallel plates, and the top one, you put your fluid in the middle, turns. And it knows the amount of force that it's turning with, so it can calculate out and produce a plot that is viscosity on the y-axis. So when you have your Newtonian behaving fluids, it's this horizontal line. When you add shear stress, shear thickening and shear thinning, you get these two curves. Remember, we want our inks to be shear thinning, which means when a force is applied to the system, the viscosity decreases. And this is important because we only want our inks to extrude when a sufficient enough force acts upon them. The second thing that our inks need to be is self-supporting. So looking back at our viscosity plot, there are certain types of fluids that when you apply a very little or no shear rate on it, again, you get a viscosity that is so high that the fluid is basically a solid. Fluids can act basically as a solids for all different types of fluids. I'm just going to specifically reference shear thinning because that is what our inks are. So any fluid that acts both as a viscous liquid and an elastic solid is called viscoelastic. And this is an important property because as we put our filaments onto the plate, so we need that viscous liquid region to flow the ink out. But then once it's on the build plate, we want it to be an elastic solid. So when we apply the second filament on top of the first, it has this temporary moment of elastic deformation where the top filament sinks into the second. However, the deformation is only temporary. That's elastic deformation. And the bottommost filament returns to its original shape. This prevents the structure from collapsing in on itself. This is your self-supporting structure. So when you plot your storage modulus and your loss modulus on a stress strain curve, you get this intersection at the apparent yield stress. Before the intersection, it tells you about your elastic region. And after the intersection, it tells you about your viscous region. So it tells you that your ink will be able to flow cleanly out of the nozzle, but it will also be able to support itself once it's on the build plate. So
All right.
going through, we know that our inks need to be shear thinning and self-supporting, right? And did you all see the Vaseline? Because that's the best real life example.
No, so let's do that.
Perfect. So this is a great place to start. So we've gone through all of the material science of what this needs to be. However, if you're anything like me, I'm a very tactile. It needs to be put into an example that I can understand. So that is actually Vaseline. So when you squeeze it, right, you have the big bottle. And when you squeeze it out, you can get it into this filament coming out of the nozzle tip, right? So that is the viscous behavior. That's because it's shear thinning. However, when you layer 2 layers of Vaseline on top of each other, you can see that the bottom layer, you can kind of see that the bottom layer doesn't collapse under the weight of the top one. You can just kind of stack them. So this is a real life, it's a very similar behavior to the material system that we are working with for our inks. So moving through the outline, we are going to talk about the ink properties. So I alluded to this when answering the questions before, so I'm going to explain it better here. Also, can you guys I don't know how to make the top go away, but basically radiation behaves in two different scattering behaviors. The first is inelastic scattering. Think of this like a car crash. Two cars hit each other with a certain amount of force, and when they hit, there's crumbling, pieces of the cars fly off. There's even a fire sometimes. So when they hit two particles, you get these secondary effects, and then you get thermal energy. This is what dominates proton and heavy ion radiation. And this is best attenuated or best stopped by low atomic density materials because the stopping power is directly proportional to the atomic density divided by the atomic mass. The other type of scattering behavior is elastic scattering. This is like bumper cars. The two particles hit each other with a force and they bounce right off. This is what dominates gamma radiation. This is best stopped by high atomic density materials because the stopping power is directly proportional to the atomic density squared divided by the atomic mass. So when we look at the periodic table of elements, our low Z materials, which are up here, I don't know if you can see my mouse as I spin it, and that best stops inelastic scattering. And then our high Z materials, which are down here, best stops elastic scattering. So when we chose to select our nanoparticle fillers, we did these with elements varying all over the periodic table. So looking at our material system, our nanoparticles include anything from our low Z material, boron nitride, our mid Z nanoparticle fillers, which are titanium and copper, and then we have our high Z materials, which are tungsten and bismuth. However, it's important to note that even though bismuth has a higher atomic number than tungsten, it has a lower bulk density, which means that tungsten behaves as our highest Z material. We use a styrene-isoprene-styrene block copolymer, and that is then modified with something called SEBS, and we fill our inks with the nanoparticle filler 50% by volume. So that allows us to create these self-supporting high-resolution structures like these lattices. And as I said, these were printed out of a 250 micron nozzle tip. So the radiation environment isn't one type of radiation hitting your electronic system at a time. It is simultaneously being bombarded with a bunch of different types of radiation, including those that span both elastic and inelastic scattering types. In order to test our radiation blocking abilities against multiple types, we created these graded radiation shields using our low Z material, 100% boron nitride, with different 25% iterations all the way up to our 100% high Z material, which is tungsten. So we wanted to see how our nanoparticle fillers actually dispersed within the filaments themselves. So as you can see, for pretty much all of our filaments, you get even dispersion of the small nanoparticles throughout. The only exception to this is bismuth, which used larger nanoparticles, and it caused this agglomeration. Additionally, because I'm going to assume I have a microscopy expert or two on here, we are aware that our boron nitride image is not as sharp as the others. The boron nitride filament is a dielectric, so it had a tendency to charge in the SEM. We are currently in the process of retaking this image so it looks just as clean as the others. So going back to the whole material science portion that was significantly longer ago than planned, we ran rheology on our ink systems. So when you look at the viscosity, right, we have this shear thinning behavior. We have that downward slope. Additionally, when you look at your stress strain curves with your moduli and your stress, you have that intersection of your storage and loss modulus, showing that we have our viscous liquid flowing region in addition to our elastic region. We did this both for the inks that I showed using one element on the periodic table and also for our graded shields, which have the same behavior, obviously, because we needed to be able to print them. So the key takeaways are that our inks are shear thinning, our inks are self-supporting. Unfortunately, the complex nanoparticle polymer interactions prevent any straightforward rheology trend to be seen, but it doesn't fully matter because it has those two key features of shear thinning and self-supporting. So as you can see, we are actually able to print our shields directly onto electronics. This is a COTS Arduino. I think we literally ordered it off Amazon. And it has two major vulnerable portions. And we were able to print directly onto the electronic itself to cover and protect these two vulnerable portions, showing that this is a low swap-C alternative to traditional shielding methods. This is all great, but we have this beautiful shield, but it kind of means nothing unless our shields actually work. So we did a radiation testing campaign. We tested 3 different types of radiation. We tested gamma rays, heavy ion, and and proton testing. We did this at UMass Lowell, Brookhaven National Laboratory, and Mass General Hospital. So quick review, just so everyone keeps everything fresh in their brains. Gamma radiation causes total ionizing dose. This is the long-term degradation of your electronics over the mission life. Because it's dominated by elastic scattering, it is best stopped by high atomic density materials. Heavy ion radiation causes single event effects, the instantaneous shutdown of your electronics. This is dominated by inelastic scattering, so it's best stopped by low Z materials. Finally, we have high energy proton radiation. This causes both total ionizing dose and single event effects. This is dominated by inelastic scattering and is best stopped by low Z materials. When we measure percent radiation block, there's 2 different metrics that we can do this with. The first is thickness. This is when we care about the S, or the size in swap. And it's literally physically how thick off the electronic our shield is. When we use thickness as our metrics, the high Z material tends to outperform the low Z material, even if it is an inelastic scattering radiation type. When you want to see that variation, it's when you use areal density, which cares about the W in swap, the weight of your shield. This measures the mass per unit area. So now that we have all the background information, we could actually dive into our radiation testing. For our gamma radiation, we opted to use a cobalt-60 source, and we had this grid set up in the radiation cave where we had a detector behind our shield. We would hit the detector without a shield with radiation and see what the dosage was. And then we'd put our shield in front of it and see what the new reduced dosage is. This allowed us to get our y-axis of percent radiation blocked. Because gamma radiation is prone to elastic scattering, our high Z material tungsten outperforms all of our other shields. And it does so in both shielding thickness and areal density. As you can see, a lot of our shields also outperform the aluminum block standard, with aluminum being what we're currently using. So what we also wanted to study is how the ratio of tungsten to boron nitride affected the percent radiation that our shields blocked. This is, remember, our blended graded shields going from 100% boron nitride to 100% tungsten. And as you can see, there is a linear relationship between the percentage of the radiation blocked and how much tungsten is present in the system. So the more tungsten in the nanoparticle filler, the more radiation that we blocked with the same thickness shield. Moving on, we wanted to test the heavy ion dose and how that affected the electronics. So heavy ion radiation causes single event effects. Single event effects are super, super, super specific to whatever electronic they're hitting. So unlike gamma radiation, where we used a detector, we opted to use an SRAM that we pre-programmed with a binary checkerboard pattern. We hit the SRAM with radiation, and we recorded the amount of errors that were caused. We then repeated this study with our shields in front of it, and we recorded how many errors the SRAM caused with the shield in front of it. This we tested for 4 different thicknesses for our copper, boron nitride, and tungsten shields, and then compared it to 4 different thicknesses of our aluminum block standard. So the way we measured this was we wanted to see what thickness was necessary for 0 errors to be thrown on the SRAM. And then what we did was we normalized this thickness to our aluminum block standard. So that's 100%. So when we use thickness as our metric, both our copper composite shield and our tungsten composite shield outperform the aluminum block standard. However, because heavy ion radiation is dominated by inelastic scattering, when we change our metric to areal density, the boron nitride shield outperforms the aluminum block standard. Either way, we are able to outperform the aluminum block standard. Finally, we did proton radiation. So we used a 60 MeV proton source, and we used a detector this time, similar to the gamma radiation testing. The way you measure proton radiation is using a Bragg peak, which is right here. The way a Bragg peak works is actually kind of counterintuitive. So as you increase the thickness of the shield, the amount of radiation hitting the detector actually increases until you get over that hump on the top called the Bragg peak. And then on the fall off, you have the linear distal region. At the distal 80%, you have a 50% decrease in particle fluence. This is a 50% decrease in the total number of particles physically hitting your detector. At the distal 50%, you have a 50% decrease in the total amount of radiation hitting your detector. So these are two very important parameters to consider depending on what mission you're doing. We tested both and then recorded both. So when we look at our 50% decrease in particle fluence, when we use thickness as our metric, our higher Z materials obviously outperform the aluminum block standard. Again, like heavy ion testing, when we change to areal density, our lower Z materials are able to outperform the aluminum block standard. The same is true when we look at the 50% decrease in total radiation dosage. The trend exists even though we have a slight shift in the thicknesses required, or the areal densities required. Finally, in our proton testing, in order to set the stage for our future work, we wanted to see how the order of our graded shields, like stacking them in front of the detector, affected the percent radiation blocked. So we stacked our shields starting from 100% boron nitride to 100% tungsten, and then vice versa. And as you can see from the bar chart, there is a statistically significant difference between the amount of radiation blocked depending on the order. With the stacking from high to low Z, so the boron nitride shield is adjacent to the detector, outperforming the other. And this actually is fully supported by literature. This set our stage for our future work. So if you remember from our stoplight chart in the beginning, our future work wanted to have the real-time gradation of our shields so we can have that benefit of stacking the shields. And we also wanted an accompanying model to select the best shield shape and composition, including gradation, for mission, orbit, and life. So in order to create a more homogeneous mixture for our gradation, we need to create an active mixing nozzle, which is what you can see in the middle. And this is done with a screw impeller, and you basically apply different pressures to the different inks. So then you can influence the amount of ink, the amount of each type of ink actually being printed. So if you look at the image, we go from black to cyan, and it's this really nice grading as you go through. Additionally, we want to see how the shield shape affects the radiation blockage. So by tapering the shield from a square shield to that nice curved edges, we have a 23% decrease in the volume and mass. So we decrease our swap penalty. The added benefit is that radiation isn't a linear phenomenon. It comes from all over in space. So we're curious to see how changing the shape of the shield affects how much radiation we actually block. But by adding these two additional degrees of freedom, we are opening ourselves up to so many unprecedented possibilities of what we can do. And in order to best figure out what direction to go to and how to create the best shield possible for a specific mission, we are hoping to create a model to help us do this. So in conclusion, if people remember from much longer ago than planned, we were able to create a direct ink writing method to print radiation shields directly onto a commercial off-the-shelf electronic, a COTS electronic. This creates a low swap alternative to traditional bulk aluminum shielding or built-in redundancies. And our inks are completely customizable. We can fill them with nanoparticles spreading all over the periodic table. And in our future work, we're going to look into how grading these shields in real time during the print will allow us more opportunities to block multiple types of radiation simultaneously. I want to thank everyone that has helped on this project, my sponsors for just sponsoring us and being great, and honestly, you guys for being the absolute best audience. So thank you.
Oh,
All
this
right.
was awesome. Oh,
Yeah.
he's here.
Okay. Yes. So I'm back. So thank you very much. Awesome talk. Thanks for sort of rolling with the punches on the outage. So we actually lost all of the internet up here at Lincoln for a period of time. But we're back. Okay, so we can open it up to questions now. So if you have come in on the Q&A, I'll get through those. And again, you can add them to the Q&A, or you can raise your hand if you want to ask live. So the first question is, you did not mention neutron radiation. Is it because it's not important at low orbit, or are you planning to deal with neutrons later?
I believe that it's part of our future direction and looking into it. With a radiation testing campaign, you are very much at the whim of what facilities are available, who's willing to take you, and how expensive they are. So I think we chose the ones that we did just due to availability. And then for proton and heavy ion radiation, they're very, very important and very prevalent. And then gamma radiation is a very good proxy for galactic cosmic rays, which is also very present.
Okay. The next question is nanoparticle size distribution an issue?
So, I mean, I'll re-pull up maybe. There we go. The SEM images, because I think it shows it really well. So as you can see with everything but the bismuth, the nanoparticles are distributed really well throughout the filament. It's when the nanoparticles are too big, they are agglomerated. So that causes a lot of difficulties with printing, actually, because it tends to clog the nozzle tip. And then just a side note on that, a lot of commercial nanoparticles, when you buy them, are not the size that they say. So we usually have to run them through SEM to make sure that they will behave the way we want them to in the filaments.
Okay, so our next question is, I might have missed it, but would you explain again why the high Z to low Z graded shield is more effective at blocking radiation than the low Z to high Z?
So it's all in the paper I referenced in literature, but basically it's when protons hit, this is the whole Bragg peak phenomenon. When they hit something like your shield, they create secondary effects. So these secondary effects are then added to the amount of radiation that is hitting your detector. When you have the low Z material adjacent to the detector, you have a larger neutron like cross section to catch it all. So it catches the secondary effects that have come through. So you're able to reduce the amount of radiation that actually hits the detector by having it there.
Okay. Can this printing methodology be utilized to create mixed lattice structures of different materials?
Yes. So that's sorry, you all get to see backwards versions of my animations now. So that is this video here. I was talking, so it was a little fast. So as it's running, I can show you. So we have one material here, and then when we move on to this one is a different material than the one used as the base, and then we're going to draw the two L's in blue, which is an additional material. So we're able to change what materials we're printing. Right now it's by switching the nozzle, but the idea is that we can also create these graded from one type to another by having this active mixing nozzle that we're working towards.
Okay. Are you guys looking to send some of these shielded on COTS components on satellite soon, or could this be a possible area of collaboration?
I mean, it's my dream too. I feel like it's definitely collaboration. Unless someone knows something I don't, but it would be really, really cool to do.
Sure.
Just from like, I came to work at Lincoln, like specifically for this project, and that would just be amazing.
Okay, we'll have to try to make that happen one day. The radiation shielding materials are most likely metals, are mostly metals, as far as I've seen. Have you ever considered to work on natural materials such as composites, like minerals for radiation shielding? Or are there other things other than just elements, metal elements that could be used?
So hydrogen is actually one of the best low Z materials for stopping radiation. Unfortunately, there is no real way to put hydrogen in a stable shield. So a lot of the time what we pick to use is because it allows us to maintain the formulations required for our inks to be printable. So that's why we select the nanoparticles we do. But I know that there have been talks about maybe diversifying what elements we are using in our prints.
Okay, but in terms of the radiation shielding properties, is it really just atomic weight that matters most?
Atomic density, yes.
Okay, and so whether it's a composite material or an element, it just as long as we get to that atomic density, that's really.
Yeah, I mean, our shields are technically composites because we have our SIS binder that we fill with a nanoparticle. They are composite shields.
Okay, okay. Thanks for that clarification. When ceramic or metal is loaded, the weight increases. Is there a weight limitation? Can you use a film that resistant to radiation instead of ceramic structures? Maybe that's.
We're not using ceramics, but
Again, just back to that discussion that we had previously, it's really atomic density that matters here. And so
yes,
that's just sort of what comes along with trying to provide shielding is that you need atomic density. But the real savings of this approach is that you put it just where you need it rather than
yes,
encasing the entirety of the electronics.
yes. So, I mean, if you compare our tungsten shield to just a giant block of tungsten, the giant block of tungsten will outperform our tungsten shield in terms of stopping the amount of radiation. The giant block of tungsten does not have the ability to be placed only over the vulnerable portion of the electronic in any shape you desire. So what we're missing out a little bit in terms of radiation blocking, which I don't know how much that is, to be very honest. We are gaining the benefit of being able to print it wherever we want directly onto the electronic. So the idea is when we do full-blown device assembly for spacecrafts, you can just add this as a step to print the shield on and then move on to the next one. We're not encasing anything in giant blocks of metal. So we're decreasing the swap penalty while increasing the customizability.
Okay, so we'll take just a couple more questions. What are the testing mechanisms besides what you mentioned about placing a checkerboard pattern on SRAM to probe single event upset? Is there work to see this implementation on FPGAs?
So we opted to use the SRAM just because we had a setup available to us here. Ideally, you would have a very similar idea with the setup where you can record, where you have a known input and you could record what that output is once it sees radiation for a bunch of different types of electronics and technologies. But because we had the SRAM setup, that's just what we opted to do.
Okay. So got a great comment from Patrick, who interned at Starlink, and he's willing to connect you to the folks at Starlink. So Patrick, if you could send us an email.
Here. I was going to say, I have my email on the last slide if he wants to write it down.
That would be great if you could do that.
Yep. Sorry. A lot of slides.
Okay.
Yeah,
And
that would be awesome. Thank you so much.
okay, have you tested the interfacial strength between the printed shields and the components? Will they survive the vibration during launch and other scenarios?
So we did mechanical testing on our shields. I can't say that it's one-to-one for what it would go through for launch, but it showed that our shields are, sorry, I'm just going to take it off my email. Okay, I'm just gonna, so it showed that our shields from the mechanical testing, they have, there we go. They have this large region of elastic deformation and then they go out. But then you can see that depending on what filler we use, that we get different behaviors. So what we would do if that becomes a reality is that we would test how to change these fillers in order to get the behavior, if not all of them behave the way we want. So like you can see the unfilled, the SIS on its own, it shows major elastomer behavior compared to something like the boron nitride.
Okay. So Avery, again, thank you very much for an excellent presentation. So this has been recorded, and maybe we'll edit it a little bit for the delay to take that out of that. there's a link, or there will be a link to the presentation on the Nano website. Just look for the Nano Explorations. And we'll send out a link as well to everybody that was on the invite list. And then we want to remind everybody or preview the next talk on December 5th by Likea Shao from the Department of Physics on campus. Should be a great talk, so mark your calendars for that. All right, so again, thank you all for joining the Nano's Exploration talk today, and we hope to see you at the next talk on December 5th.
Thank you.